Okay, we're back to group theory. So we're starting the real subject of group theory. And I'm going to review what I did on Monday, and we will continue from there. Are there any questions about what we covered on Monday or anything else? Okay. If not, then we want to talk about groups, subgroups, and cosets. So we have a group G with an identity E, and I recall that we usually write groups multiplicatively, right? You need to be able to translate multiplicative notation to additive notation. So what that means is, for example, if you take the associative law, the multiplicative way of describing associativity is xy times z is x times yz. This is multiplicative, using multiplicative notation. How do you translate this to additive notation? The times become pluses, so this becomes x plus y plus z equals x plus y plus z. So this is what I mean by saying you can translate a multiplicative statement about groups to an additive statement about groups. So all it means is you're replacing each times sign with a plus sign. But you have to know how to do that. And in group theory, you don't do everything twice. You don't write things down multiplicatively and additively, because it's easy to go from multiplicative to additive notation, or conversely in the other direction. Okay. So we say a subset H of the group G is a subgroup if, first of all, the identity element, E, of the group is contained in H, and H is closed under multiplication and inverses. So what that means is H itself is a group. It's a group contained in the larger group. So for example, if we take Q star to be all the non-zero rational numbers, fractions, this is a multiplicative group. And if you take all positive means strictly greater than zero rational numbers. Every positive number is non-zero, so Q, the positive rationals form a subset of all the non-zero rationals. And 1 is the identity element under multiplication for rationals, and it's positive. And this set is closed under the product of two positive numbers is positive, and the inverse of a positive number is positive. So the positive rationals are a subgroup of the rationals. As an example of an additive group and subgroup, you could take the group Z of all integers. That's an additive group. And we have the subgroup, for example, of 3Z, which is all multiples of 3. The identity is 0. 0 is a multiple of 3. The sum and difference of multiples of 3 is a multiple of 3, so this is a subgroup. What's a subgroup of 3Z? Well, for example, 6Z. 0 plus or minus 6 plus or minus 12 plus or minus 18. This is a subgroup of 3Z and a subgroup of Z, because every multiple of 6 is a multiple of 3. What about 42Z? That's 0 plus or minus 42 plus or minus 84 plus or minus 126 and so forth. This is all the multiples of 42. Every multiple of 42 is a multiple of 6. Every multiple of 6 is a multiple of 3. Every multiple of 3 is an integer. So we actually have this chain of subgroups. Z contains the subgroup 3Z, contains the subgroup 6Z, contains the subgroup 42Z, for example. There are lots of subgroups in the universe. What about for a finite group? Suppose we take S3, the permutation group. And you take, for example, H. So this is my group G. For H, I take the identity permutation and the transposition 1, 2. This is a subgroup. Because it's a subset of S3. It contains the identity, and it's closed under multiplication, and it contains the inverse of each element. So it's 1, 2 times 1, 2 is the identity. Okay. Interchange 1 and 2, interchange them again, you're back where you started. So this is closed under multiplication, and it contains the inverse of each element. The inverse of 1, 2 is 1, 2. Well, that's subgroup H1. Or we can take the subgroup consisting of the identity, the 3 cycle 1, 2, 3, and this 3 cycle 1, 3, 2. So if we call this sigma, this is actually sigma squared, which is also the inverse, sigma inverse. And this is a subgroup with 3 elements contained in the permutation group. Mm-hmm. Any questions about this? Let's look at one more example. Suppose we let gamma n, this is a capital Greek letter gamma, be the cyclic group of order n. So what does a cyclic group mean? It's a group which has exactly n elements. One is the identity. There's an element x, x squared, x cubed, up to x to the n minus 1. And multiplication is defined as follows. We defined x to the 0 is e. So if you have x to the I times x to the j, this is x to the I plus j, so long as I plus j is at most n minus 1, and it's x to the I plus j minus n if I plus j is greater than or equal to n. So for example, what is the cyclic group of order 4 look like? It consists of 4 elements, e, x, x squared, and x cubed. And what is the multiplication table? X means x to the first power. So e times anything is the anything. X times e is x. X times x is x squared. X times x squared is x cubed. X times x to the fourth. 4 minus 4, that's x to the 0, which is the identity. X squared times e is x squared. X squared times x is x cubed. X squared times x to the squared is x to the fourth, which is the identity. X squared times x cubed. 2 plus 3 is 5. 5 minus 4 is 1. X squared times x cubed is x. Because you can also see it like this. X squared times x cubed is x to the fifth, which is x to the fourth plus 1, which is x to the fourth times x, which is e times x, because x to the fourth is e, which is x. X cubed times e is x cubed. X cubed times x is x to the fourth, which is e. X cubed times x squared is x to the fifth, which is x. X cubed times x cubed is x to the sixth. 6 minus 4 is 2. So this is the multiplication table for the cyclic group of order 4. And if I take H to be the set consisting of just x and x squared, this is a subgroup. It's closed under multiplication, x squared times x squared. That's x to the fourth, which is the identity. So x squared inverse is x squared. This is closed under multiplication and contains the inverse of each element. So this is another example of a group and a subgroup. Any questions about this? These are all fundamental concepts in algebra. Okay, so what is a coset? We have a group G, a subgroup H, and an element X in the group G. So we define the left coset. It's called left coset because you take H and you're multiplying it on the left by X. So this means this is a subset of G. It's everything of the form X times H, where H is in the subgroup H. And we have the right coset, HX, where you take everything in the subgroup H and multiply it on the right side by X. And in general, if the group is not abelian, these will be different. They could be the same, but they can also be different. So let's look at an example. Suppose I take G to be equal to S3 and H to be the subgroup consisting of the identity and the transposition 1, 2. And suppose I take X to be the transposition 2, 3. So what is XH? This is X. So there are two elements in H, and I multiply each of them on the left by X. So this is X times E and X times 1, 2. x is 2, 3. And when I multiply it by the identity, it's still 2, 3. And this is 2, 3 times 1, 2. So this is the transposition 2, 3. And 2, 3 times 1, 2 is the 3 cycle 1, 2, 3. Because this sends, oops, sorry, not the 3 cycle. 3, 2, 3, 2, 1. Let me write it correctly. Because this is the same as 2, 3 is the same as 3, 2. 1, 2 is the same as 2, 1. And when you put that together, you get 3, 2, 1. So 3, 2, 1. Because you see, this sends 1 to 2 to 3. So 1 goes to 3. 2 goes to 1. And 3 goes to 2. So these two group elements, that's the left coset XH. What about the right coset? So this is E times X and 1, 2 times X. So E times X, X was 2, 3. And 1, 2 times 2, 3. So this consists of 2, 3, and this is the 3 cycle, 1, 2, 3. So this is the left coset, this is the right coset, and notice in this instance that the left coset is not the same as the right coset, because 3, 2, 1 and 1, 2, 3 are different permutations. So think about that for a minute, and then spend a couple of minutes right now with some paper working out the following. For the same group S3 and the same, so we have G be equal to S3. Suppose I take H to be the subgroup consisting of the identity and the 3 cycle 1, 2, 3 and the 3 cycle 1, 3, 2. That's a subgroup. Let X be equal to the permutation 1, 3. Compute the left coset XH and the right coset HX. So spend a minute now with some paper to do this calculation. And then I'll do it. But these are compared to things that will come later, very simple group theory calculations. And so it's important to be able to do them. So let's see. Let me do the calculation here. So G is S3. H is the 3-element subgroup consisting of the identity, the permutation 1, 2, 3, and its inverse, which is the permutation 1, 3, 2. And X is the transposition 1, 3. So what is the left coset? You multiply each of these permutations on the left by X. XE, X times 1, 2, 3, and X times 1, 3, 2. So X times E is just X, which is 1, 3. X times 1, 2, 3, that's 1, 3 times 1, 2, 3. X times 1, 3, 2 is 1, 3 times 1, 3, 2. What is that? Well, this is 1, 3. What is this? This sends 1 to 2. 2 goes to 3, goes back to 1. 3 goes to 1, goes to 3. So this is just the transposition 1, 2. What is this? 1 goes to 3, goes to 1. 2 goes to 1, goes to 3. 3 goes to back to 2. So this is the set of the 3 transpositions. That's the left coset. What is the right coset? I multiply each of the permutations in H on the right by X. So EX, 1, 2, 3 times X, 1, 3, 2 times X. So E times X is X, which is 1, 3. This is 1, 2, 3 times 1, 3. This is 1, 3, 2 times 1, 3. So this is 1, 3. What is this? This sends 1 goes to 3, goes back to 1. 3 goes to 1, goes to 2. 2 goes to back to 3. This is the permutation 2, 3 or 3, 2. Here 1 goes to 3, goes to 2. 2 goes back to 1. 3 goes to 1, goes to 3. So this is also the set of the 3 transpositions. So in this case, it happens that the left coset equals the right coset. In the previous example, that wasn't true. In this example, it is true. That just says sometimes the left coset equals the right coset. Sometimes it doesn't.
Hello, Professor.
Yep.
Can you go back to that? Could you for the mappings of 1, 2, 3, and 1, 2, could you show me again how'd you determine that?
So I don't see a 1, 2, 3 times 1, 2 anywhere.
Oh, so you see how you do EX and then 1, 2, 3X and then 1, 2, 3. I mean 1, 3,
Right.
2X, the second row, yeah. The mappings
So
for that.
so multiplying everything on the right by 1, 3. 1, 3, 1, 3, 1, 3. You want to know how I computed this?
Yes.
All right. So 1, 2, 3 times 1, 3. These are functions. So, and this is composition of functions. So let's look at 1. This sends 1 to 3, and then this sends 3 back to 1. So if I write this composition in standard form, 1 goes to 1. This sends 2 to 2, that doesn't change 2, and then 2 goes to 3. So 2 ends up at 3. 3, this sends 3 to 1, and this sends 1 to 2. So 3 ends up at 2. So this is what? This is just the transposition 2, 3. Right? 1 goes to 1, 2 goes to 3, and 3 goes back to 2. So 1, 2, 3 times 1, 3 is 2, 3, which is the same as 3, 2. Right? It's the same thing.
Okay, I see it. Thank you.
Yeah, no, this is very important to be able to do these calculations correctly.
Okay. No, but yeah, I see the mapping now. It was just a bit confusing the way it was set up, just side by side.
Mhm.
All right, thank you.
Well, but that's what you do in calculus, right? In calculus, you have, a function f and a function g. The composition is fg, and it's defined by fg of x is f of g of x. Right? It's exactly the same thing you did in calculus every semester when you compose functions. It's no different at all. So we have left cosets and right cosets, and we let G/H be the set of all left cosets of the subgroup H and the group G. This is all X times H for all X in G. H is fixed. You look at all possible left cosets, this is a set of them. And H/G like this is the set of all right cosets. So this is everything of the form H times X on the right, where X is in G. And the cardinality, this is the number of left cosets, that is, the size of this set is what is called the index of H in G. And it's denoted square brackets G:(H) like this. So the index of a subgroup is the number of left cosets. And you might say, what about the number of right cosets? And we will show later that it's always exactly the same, that the number of left cosets equals the number of right cosets. But at this point, all we need is a definition of the index, and we define it in terms of the left cosets. And one of the most important theorems in mathematics is a theorem of Lagrange, which says that the left cosets of a subgroup partition the group, and in a very, 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 very nice way. So this is what we want to show. So I claim the left cosets XH partition G. So again, you have to remember what everything means. A partition of a set is a collection of subsets with the property, two properties. Every element of the set belongs to one element of the partition, and the elements in the sets in the partition are disjoint. They have no elements in common. So you have a group G, and it's divided up into a finite number of pieces, which are all going to be cosets. So what this claim means is the following. Every element of G belongs to some coset, And two cosets are either the same, equal, or they are disjoint. They have no elements in common. So first of all, you notice we have H, a subgroup of G, means, first of all, the identity element is in H. So for all X in the group, we have X, which is X times E, is in the left coset. So every element is in some left coset. So we can say that, therefore, G is the union of all of the left cosets. Every left coset, every element belongs to some left coset. This is the obvious one. So G is the union of these left cosets. And what I must show is that if I have two left cosets, X1, XH, and YH, and if their intersection is not empty, that is, I have two left cosets and they have some element in common, then, in fact, they are equal. That means they're the same set. And how do we prove that? So suppose Z is some element in the intersection of these two cosets. So then if Z is in the intersection of two sets, that means it's in both of them. So if Z is in XH, this means there is an element, I'll call it Y1 in H, such that, I'll call it H1, just to emphasize the fact that it's in H. There's an element H1 in H, such that Z equals X H1. And because Z is also in the left coset YH, there is an element H2 in H, such that Z is equal to Y H2. Well, Aristotle said that things equal to the same thing are equal to each other. So therefore, XH1 equals YH2. Which means if I multiply on the left by H1 inverse, X is equal to Y H2 H1 inverse. So take a look at this and let me know if there are any questions. This is sort of a key thing. So it follows that for all H in the subgroup H, X times H is Y H2 H1 inverse times H. So XH is Y times this element. This is something in H, because H is closed under multiplication and taking inverses. So this is in the left coset YH. For all H in the subgroup H, which means the left coset is contained in the right coset. Now, when I did this multiplication, I could also have multiplied on the right by H2 inverse. and I would have gotten y is equal to x h1 h2 inverse. So for any h, y h would be h x1 h2 inverse h, and that would tell us that, so this is a completely symmetrical argument, that the left coset yh is contained in the left coset xh. And the definition of two sets being equal is that each is contained in the other. So xh equals yh. So if two cosets are not disjoint, if they have an element in common, then in fact they're equal. So this tells us exactly, if I look at the group G and I look at all the left cosets, every element is in one of these left cosets, and these left cosets are pairwise disjoint, so they do partition the group G. So I've just given a proof of the theorem the left cosets of H partition the group G. Now we can prove Lagrange's theorem. Lagrange's theorem applies to a finite group. That G be a finite group and H a subgroup of G. Then the index of G and H, as the number of left cosets, is in fact the number of elements, the order of G, divided by the order of H. And I remind you that for any set X, when you put absolute value signs around it, this means the number of elements in X, right? Or the cardinality of X. Cardinality is just a mathematical word for number of elements. And another way of saying this is that the order of G is the index of H and G times the order of H. And these are all positive integers. So another way, so this statement means, so this is actually a corollary, if you like. In a finite group, the order of a subgroup divides the order of the group. Because the order of G is a multiple of the order of H. That's just the definition of divisibility. So these statements together form what is called Lagrange's theorem. And let's prove this. So remember, here's our picture. Here's G. We have a subgroup H. So G is finite. The cardinality is less than infinity. We can go all the left cosets. So G mod H is all the left cosets. One of them, of course, I can take X to be the identity. E times H is just H. So I have H. And let's say, well, X2 times H, X3 times H, XK times H. Right, so G mod H is certainly finite. It's a finite set of left cosets because you have a finite set, you're dividing it up into pieces, non-empty pieces, and you can't have infinitely many non-empty subsets in a finite set. So suppose we let G mod H have order K. They're K left cosets. Say G mod H consists of exactly the following cosets: X1H, X2H, up to XKH. And these are pairwise disjoint. So G is the union of these K cosets. And the fact that they're pairwise disjoint means the number of elements in G is the number of elements in X1H, the number of elements in X2H, and so forth. It's the sum of the sizes of these sets. But I claim that every left coset has cardinality or order H. They all have the same number of elements. And what is the proof of this claim? Well, suppose I define a function f from h to xh by f of h equals xh. This is 1-to-1 and onto. It's certainly onto because every element in the left coset is of the form xh, and h gets mapped to xh. And it's 1-to-1 because if xh1 equals xh2, you divide by x and you get h1 equals h2. So this is the proof that this function is 1-to-1 and it's certainly onto. So they all have the same number of elements. So this is just equal to the size of h plus size of h, k times. That's k times the cardinality of h. And that's the end of the proof, because k is the index. Right? K is the index. So we just proved that the order of G is the index times the order of H. Now, there are a few better ways to spend your time than studying over and over the proof of Lagrange's theorem. And you definitely need to be able to take a plain blank piece of paper and without looking at your notes, to find all the terms that go into Lagrange's theorem, left coset, index, subgroup, and so forth, and prove the theorem. This is one of the fundamental things you have to learn in this course. You can't pass algebra just by doing the computational problems. You have to know how to prove basic results, and this is really a key one. Any questions about this so far? So actually, all of this is a review of what I did on Monday. And let's go a little bit further. Let's go back to cyclic groups. Finite cyclic groups of order n. So a finite cyclic group of order n looks like, it doesn't matter what variable we use for the, let's say x squared, x cubed, up to x to the n minus 1, with, so x to the n is x to the 0 is the identity, and x to the I times x to the j is x to the I plus j mod n. This is a finite cyclic group. And we just proved by Lagrange's theorem the order of a subgroup divides the order of the group. So if we let G be the cyclic subgroup of order n, so the cardinality of G is n, and H is some subgroup of G, then the order of H, I'll call it D, divides n. So, for example, the cyclic subgroup gamma 4 contains no subgroup of order 3 because 3 does not divide 4. So if I were to ask you, what are the subgroups of a cyclic subgroup of order 40? What are the subgroups of the cyclic group of order 40 of order 6? The answer is none, because 6 does not divide 40. Lagrange's theorem says the order of a subgroup divides the order of a group. If that condition is not satisfied, there's no such subgroup. If that condition is satisfied, there still might not be such a subgroup. We don't know, but it's definitely, but without the divisibility condition being satisfied, there is no subgroup. Cyclic groups are particularly nice because for every divisor of the order of the group, there is always one and only one subgroup of that order. So let's see if we can prove something like that. For every positive divisor D of n, the cyclic group gamma n contains a subgroup of order D, and in fact, it contains exactly one subgroup of order D. And it's easy to write down what that is. Suppose we let gamma n be x e x squared up to x to the n minus 1. And if D is a divisor of n, let n equal D times Q. Suppose I let H be the subgroup of gamma n consisting of all the powers of x to the q. E, x to the q, x to the 2q, x to the 3q. I can get up to x to the d minus 1 times q. The next power of q would be x to the dq, but x to the dq is x to the n is the identity. And this is a subgroup of order D. It contains exactly D elements and is closed under multiplication. X to the iq, x to the jq is x to the iq plus jq, which is x to the q to the power I plus j, plus iq plus jq is q times I plus j. So the product of two powers of x to the q is another power of x to the q. So this set is closed under multiplication.
Here's something I found on the web. According to Quora.com, actually, the letter Q is indeed used to represent the word Q.
Okay. Yeah. Powers of x to the q, or products of powers of x to the q, are powers of x to the q. This set is closed under multiplication, and it contains the inverse of each element because x to the iq times x to the d minus I times q. This is for 0 less than or equal to I less than or equal to d minus 1. So d minus I is between 1 and d. This is x to the iq plus d minus I times q. That's x to the dq, which is x to the n, which is the identity. So this set contains the inverse of each of its elements. This is a subgroup, and it has exactly order D. So this proves that the cyclic subgroup of order n contains at least one subgroup of order D. And why is there exactly one subgroup? So that's an interesting question. So let H be a subgroup of the cyclic group gamma n. So H is contained in the set of powers of x. Suppose I let Q be the smallest, be the smallest. So there are two cases, of course. Let me just make this clear. So case one, which is sort of the trivial case, H is the subgroup that just contains the identity. the set containing the identity elements, a subgroup of any group, because E times E is E. It's closed under multiplication. The inverse of the identity is the identity. And H is this, which is the same as x to the 0. It's the subgroup generated by x to the 0, if H is just the identity. So the more interesting case, it's H is not just the identity, which means H contains x to the I for some positive integer I. H is a subset of this set. It contains more than the identity, so it contains at least one of these elements, and these all have positive exponents. So in this case, when H is not just the identity, that Q be the smallest positive integer such that x to the Q is in H. That x to the, let's say, that x to the m be in H for some m. Divide m by Q. So you get m is Q, let's say D, let's say QJ plus R, where 0, the remainder is between 0 and Q minus 1. Now, we know that x to the m is in H, right? And we know that x to the Q is in H, which means that H is closed under multiplication. So x to the Q to the power J, which is x to the QJ, is in H. If x to the m is in H and x to the QJ is in H, then x to the m times x to the QJ inverse is in H. X to the QJ inverse is x to the minus QJ. This is x to the m minus QJ. And m minus QJ is equal to r. X to the r is in H. So what does that tell us? It tells us that x to the r is in H. R is strictly smaller than Q. But Q is the smallest positive integer that's in H. And if R is less than Q and positive, it can't be in H. X to the R can't be in H. So therefore, R has to be 0, and M is Q times J, which means the only elements in the subgroup H are x raised to a power that's a multiple of Q. So H is the set of all powers of x to the Q. And let's see. Well, we also know E is in H, so that M, which means E is equal to x to the MQ for some M, because everything in H is a power of M. Actually, this is correct, but let me say this slightly differently. So H contains the infinite sequence of elements x to the q, x to the 2q, x to the 3q, x to the 4q, and so forth. But H is a finite set. So this infinite sequence of elements, they can't all be different. So there exist integers I and j with I less than j, and x to the I equals x to the j, because x to the iq equals x to the jq, which means the identity is x to the jq times x to the minus iq. I'm just multiplying on each side by x to the minus iq. This is x to the j minus I times q. So j minus I is a positive integer, and x to j minus I times q is the identity. So if they're positive integers, m, where x to the mq is the identity, then m be the smallest positive integer such that x to the mq equals the identity. So that means that h, which is the powers of x to the q, you get x to the m minus 1q, and these are all different because if they were, two of them were the same, x to the something q would be the identity for an integer less than m. The next power of q would be x to the mq, that's the identity. So H is just this set. This is a cyclic group itself of order m. Right, generated by x to the q. I'll use this brackets to mean just that this is just the powers of x to the q. So what we proved, and we just needed a little bit of elementary number theory to prove this, is if you take a cyclic group of order n, any subgroup is going to be generated by an element of the form x to the q, and m times q is equal to n. Q divides n. Well, this group has order m. M divides n because the order of a subgroup divides the order of the group. And mq is equal to n. So this may be a little bit a lot to absorb the first time you see it. And I'll make sure that it's written out very completely in the notes, but this is a basic fact in group theory about cyclic groups. Here I've written my cyclic group multiplicatively. Let me point out that if you write a cyclic group additively, it's just congruences that we studied a bit. So let's take an additive example. Additive group example. Take G to be the integers. Take H to be the multiples of M. What are the left cosets? G mod H or Z mod MZ. Because G is Z and H is MZ. This is everything of the form X plus MZ. It's all, but this is a congruence class. And They're exactly M congruence classes. 0 plus mz, 1 plus mz, 2 plus mz, up to m minus 1 plus mz. And I claim this is a cyclic group, but it's additive. What does an additive cyclic group look like? If I have a cyclic group which is additive, it looks like 0. So instead of the powers of an element x, it's the multiples of an element x. 0x, 2x, 3x, up to m minus 1 times x, and m times x is 0. That's what an additive cyclic group would be. And that's exactly what we have here, where x is 1 plus mz. 2x is 2. Well, it's 1 plus m, it's x plus x. 1 plus mz plus 1 plus mz is 2 plus mz. In general, k times x is k plus mz. And m plus mz, that's m times 1 plus mz, is m plus mz is 0. 0 plus mz, mz. So the set of congruence classes is an additive cyclic group. The thing we're taking the multiples of is called a generator. With generator x equal 1 plus mz. So a lot of what we did when we were talking about elementary number theory, and the reason we spent time doing that is because it gives a very important example of a cyclic group written additively. This group of congruence classes modulo m. Okay. Let me make a couple of other remarks. In general, let G be a group and let S be a subset of G. Before I do that, I'll make a more general remark. Let G be a group and let's call it script H, be a set of subgroups of G. Then if I take the intersection of all of the subgroups in this set H is also a subgroup of G. Let me call this a theorem. You have a collection of subgroups of a group, their intersection is a subgroup. Well, what is the proof? Well, first of all, for every element, every subgroup H in this collection of subgroups, every subgroup contains the identity. which means, let me call this thing H star. If E is in every one of these sets H, it's in the intersection. So E is in the intersection of the subgroup. So this set contains the identity, which is the first condition for a set to be a subgroup. I want to show H star is closed under multiplication. So let X and Y be in H star. That means X is in H and Y is in H for every one of these subgroups H, which means X times Y is in H for all H and H star. And that means XY is in the intersection. So H star is closed under multiplication. And what about inverses? If X is in H star, then X is in H for every one of these subgroups, which means X inverse is in H for all these subgroups, which means X inverse is in H star. And that's the end of the proof. I proved that if you have a collection, a set of subgroups of a group, and you look at their intersection, it contains the identity, it's closed under multiplication, and it's closed under taking inverses. So it's a subgroup. And it doesn't matter whether the collection of subgroups is finite or infinite. Let's look at an example. Suppose I take the subgroup gamma 12, the cyclic group gamma 12. So this is E, X, X squared, X cubed, X to the fourth, X to the fifth, X to the sixth, X to the seventh, X to the eighth, X to the ninth, X to the 10th, X to the 11th. And we have a subgroup H1, which is, for example, E, X to the fourth, and X to the eighth. This is a subgroup. It's closed under multiplication. It's just powers of X to the fourth. Actually, let me take a bigger subgroup. Suppose I take the subgroup generated by yeah, I want a better example. Let's take the subgroup generated by X squared. So E, X squared, X to the fourth, X to the sixth, X to the eighth, X to the 10th. So these are the powers of X squared. So this is X to the 2I, I going from 0, 1, 2, 3, 4, 5. That's a subgroup. Suppose I take the powers of 3. So this is the subgroup x to the 3j. J 0, 1, 2, or 3. So this is a subgroup of order 6. This is a subgroup of order 4. What's the intersection? Well, you just look, what elements are in common? They both contain E, and they both contain x to the 6th. So the intersection of these two subgroups is another subgroup. That's an example. So now let's go back to what I started to say. Let G be a group and let S be a subset, not a subgroup, but it's a subset of G. I'll call a script S be the set of all subgroups H of G that contain S. So for example, G is in S because G is the whole group. G contains S. So this is the set of all the subgroups that contain S. What we call the subgroup of G generated by S. It's the smallest subgroup of G that contains S. And this is just the intersection for all H in script S of the subgroups. So we proved that the intersection of any set of subgroups is a subgroup. So as a special case, if we choose a subset of G and we look at all the subgroups of G that contain S and take their intersection, that's going to be a subgroup. And we call that the subgroup generated by S, which we usually denote by S in these angular brackets. That's the subgroup generated by S. And the basic special case is the following, that X be in G. If we take the set S to be just the single element X, then X in brackets is the subgroup generated by X. So let me write down a few examples of this. Suppose I take G to be the integers and X to be the number 7. What is the subgroup generated by 7? It's just a set of all multiples of 7. Or 7Z. So this subgroup of Z is the subgroup generated by 7. Suppose I take G to be the integers mod 12. So this is the set of all congruence classes X plus 12Z. X is, say, an integer from 0 to 11. What is the subgroup generated by the congruence class 3 plus 12Z? It's just a set of all multiples of 3 plus 12Z. That's going to be 12Z, 3 plus 12Z, 6 plus 12Z, 9 plus 12Z. So this is the order of G is 12. The order of H is 4. Of course, 4 divides 12. Suppose I take G to be S3 and X to be the permutation 1, 2, 3. Call it sigma. The subgroup generated by sigma is the identity sigma and sigma squared, because sigma cubed is the identity. That's E 1, 2, 3 and 1, 3, 2. That's the subgroup generated by sigma. If I take tau to be the transposition 1, 2, the subgroup generated by tau is just E and tau. Tau squared is the identity. If I take G to be the cyclic group of order n, and I take, so this is going to be E x squared to x to the n minus 1. Suppose I take an element, I better not call it x, I'll call it y, equal, let's make this concrete, like gamma 12. So this goes up to x to the 11. What's the subgroup generated by x cubed? It's going to be E x cubed, x to the 6th, x to the 9th. You notice this and this are essentially the same thing. This is an additive group, this is a multiplicative group, but they look exactly the same. You know, the word we use to describe that is isomorphic. So this additive group and this multiplicative group are isomorphic. So let G be a group, let X be an element in G, and let H be the cyclic subgroup of G generated by X. So this is a subgroup. And what we call the order of a group is the number of elements in a group. What we call the order of the element X is exactly the order of the cyclic subgroup generated by X. So for example, when we had G equal to the cyclic subgroup gamma 12 and X equal to, or Y equal to X cubed, the cyclic subgroup generated by X cubed was E X cubed, X to the 6th, X to the 9th. So the order of X is the order of X cubed, which is equal to 4. So we say X cubed, the element X cubed has order 4 in the group gamma 12. What is the order of X to the 8th in the group gamma 12? So what is the subgroup generated by X to the 8th? It's all powers of X to the 8th. E, X to the 8th, X to the 16th, X to the 24th. But of course, what is X to the 16th? In the group gamma 12, X to the 16th is X to the 4. equals 16 is 12 plus 4. X to the 24 is x to the 12 squared. That's e squared, that's e. So x to the 8th, the subgroup generated by x to the 8th is this subgroup. So x to the 8th has order 3 in the group gamma 12. Well, it's getting a little bit more serious, I guess, in algebra, because we've looked at numbers of examples of groups, but the idea of group theory is to prove general properties that all groups satisfy, and not just those in some special examples that we look at. And really, for the rest of the term, what we are going to be doing is proving theorems like this about groups and looking at examples to show, to make the general theory concrete. Are there any questions about this? Again, look over the notes. This will also be posted on Zoom, on YouTube in a short time. But this is all very basic, very important group theory. And you need to spend a fair amount of time studying it.